大家好，我是王不老说半岛。Hi, folks. Today, I would like to continue my discussion, especially about process technology. Most of my talk are related to process, you know, with a selective view about design, layout, something like that. But uh, that's my forte. I would like to talk about process more. And today, my topic is hot topics about N or P on top. I'm going to present three cases: silicon, germanium, and then gallium nitride silicon, and then complementary nanosheet FET. The question is, who gets on top this time, N or P? And it turns out they are all different, and they are different because of various reasons. And that's the point of my discussion here. Let's continue. Today, my icebreaker is that when I talk about NOP on top, something comes to my mind is the Shakespeare's Hamlet's soliloquy, to be or not to be, right? To live or to die, that's the question. Whether this is this nobler in the minds to suffer, I would say this is stress engineering, right? So this is my personal favorite quote. And today, the first case I'm going to present to you is gallium nitride CMOS on high resistivity silicon 111. This is a dream of Intel. They've been doing that for the last 15 years or so. Pretty good progress. And they compare with the Raytheon. Right? Take a look at the Intel's publication on this topic. The idea is that they would like to combine all these devices, right? The ADMOS, HAMP, and then the gas HBT, and again, gallium nitride HAMP, all to one single devices, which is gallium nitride with an enhanced mode transistor. They need a CMOS, by the way. They need a CMOS. But to make a CMOS and also to be enhanced mode. So this one will be a SoC, silicon a system on chip. All right. So this is the idea. Of course, they use their process technology expertise in this field. Right. They could use work function metal to tune the enhanced mode, to tune the gallium nitride, which is a naturally depleted device, into a enhanced mode, which is VT greater than 1. And that will be the goal of this device. And high-K metal gate, you know, the Intel invented this process, and to locate leakage and scalable, they want to put it onto a 300 millimeter silicon. They want to replace this bulky, everything separate into one package, one device per se. And you could see that they also find out that uh, you need a CMOS. MOS only is not good enough. MOS only, the number of gates will be a lot fewer you can do. You really need a CMOS to be commercially viable, and then so as to compete not directly with silicon CMOS, but in the SoC field they are interested in. This is a good companion to silicon CMOS they're doing. And of course, it's not an easy thing, right? The first question come to mind is that why silicon 111? They want to do, if you look at the picture here, the gallium nitride here had to sit on a piece of wafer, right? 300 millimeter wafer. So the option is that you could have multiple options, of course. If you do the survey on the industry, gallium nitride currently can be done on silicon carbide or sapphire. But these are all like 6 inches, 4 inches. Silicon carbide, you can do 6 inches. Wolfspeed can do, 8 inches. Wolfspeed can do that. And sapphire pretty much are 4 to 6 inches only. But these are good. These are pretty good substrates. And then look at the lattice mismatch versus thermal mismatch. Right? You could look at you could check the sapphire is pretty good at the thermal mismatch, smaller thermal mismatch. And silicon carbide, of course, has a lattice mismatch very small to gallium nitride right here. You can use aluminum nitride, of course, but that's another story, right? So gallium nitride, you should use these materials. And then the silicon 111 is the lattice constant is like 3.85 Armstrong. That's not too far with gallium nitride. If you compare with the silicon 100, well, that's about 5 or more, right? That's close to 6 Armstrong. So this is silicon 111 in comparison to 100 is a better one. Even though you can see that the lattice mismatch is large, the thermal mismatch is large as well. And this is all in comparison, right? Compared with the silicon carbide, which is very good thermal conductor, and then the sapphire, which is a smaller. I'm sorry, the lattice constant is about the same, but the thermal mismatch is small, is a lot smaller for sapphire. But these are expensive, and there's no 300 millimeter. Okay, so obviously, Intel we have to use silicon 111. It's a little bit expensive, but 100 for sure. But that's the best option right now for you. How about the what about just a PMOS, gallium nitride PMOS? This is a no-go. The reason is pretty simple, right? The whole mobility of gallium nitride is less than 50. You see that the table on your left is less than 50. The whole mobility is very poor. And doping, don't forget about the doping. It's very poor too. It's very hard to dope gallium nitride with a p doping. The N doping, on the other hand, is much easier. It just happened to all the three files. It just or you get or three or gallium nitride or this similar material. Everybody's going for N, but P is really really hard. But by nature, is this actually is the nature. And if you could also take a look at the benchmarking. When you do a comparison, you always do a benchmarking. This is a desired zone. And then everybody else compete with each other, right? So this is one of the applications. This is Intel applications. Oh, we're pretty good. I own it's very high. I off it's about 10 to the fourth, but it's still not good enough. Not good enough. Right? There's a lot of work to be done, right? So this talk about PFET. So PFET I say will be a no go, no way, right? And then so Intel, the plan is here. It's pretty much summarized in this one picture. It's just different process. It's a P silicon on N FET, on gallium nitride FET, on 300 millimeter silicon 111. This is the material aspect of their technology. Then you can see that pretty much there's a layer transfer. There's a layer transfer, which means, and then they finish the end process. First of all, the epitaxial growth gallium nitride with a buffer, a couple micron buffer. Then about 4 to 6 micron, and then you put a gallium nitride on top, and then you build your device. This is high-K metal K, and then when you finish your NFET, you want to put a P on top. How do you put a P on top? Then there are options. There are three options: polysilicon, silicon 100, or silicon 111. So this is what we're going to talk about. And and then of course, the goal is to bond them with a bonding oxide, a layer transfer, or another SOI, or something. Right? This go one by one. The polysilicon channel is one of them. The benefit is that here on the right hand side there are 4 figures. There are 4 options you could do. And polysilicon is that you do a layer transfer You don't need to do a layer transfer. I'm sorry. This is an isolation. You have put an oxide after you build your N, and then you put deposit silicon on top. That's the best case. You don't need to do a layer transfer. You don't need to put SOI. You just put an oxide on top, and then you layer a silicon channel on top. Unfortunately, the way nature works is that it's done by CVD process or at best ALD. No matter what you do, the best case will be a polysilicon, right? And then when you do a polysilicon, see here, and then you anneal it, you recrystallize. Initially, you may be amorphous, but eventually you recrystallize it with high temperature, right? Then you form a polysilicon. And it seems okay. Then you put your devices on top of high-k metal gate, source and drain, and all that. But what's the problem? Why it says no go or put a set face here then? The reason is that polysilicon has a very bad mobility. And you can look at this curve on the right-hand side, right? For the different doping in this, forget about doping. And for the low doping, so for low doping, you can see that it dropped. Okay, the single crystal, uh, the mobility of carrier uh, dropped by 1 order magnitude here to here, right? 1 order magnitude. It doesn't matter what kind of uh, doping concentration is dropped pretty dramatically. And D here is a grain size. I mean the grain size, different grain size. And then, no matter what you do, the small grain size, the large grain size, they all drop by 1 order magnitude. Okay, so that's a problem. And then the reason, the fundamental reason is that the mobility, the carrier moving inside a crystal is very sensitive to grain boundary. It doesn't like grain boundary. You see the grain boundary will act as a attractive force. And so it will attract the carrier and then there's more scattering around. Then that's what the problem. The grain boundary scattering caused the degradation of mobility. And polysilicon is another problem. It's sensitive because the EG, if you look at that, the different crystal orientation has a different the energy band gap. You see that depends on thickness. It has some different band gap. You look at it. Well, is it big? It's not too small. It's a couple hundred millivolts. And the point is that you can't control it. It's random. So that makes your VD control very hard. So that's the reason, and polysilicon is not good. Okay, for I say for a channel, the cheap material, yes, but for this high-end material, no. Right? If a VT control has to be couple within couple hundred millivolts, like 10 millivolts, then you cannot do it. You had if your VT is like 10 volts, then you're fine, right? If you can pull up with the mobility degradations. By the way, the ultra thin silicon has a BD control issue. If you look at the graph uh, on the right hand side, this is for the nanowire, pretty similar for uh, the thin film as well. You can see that the surface functions has a strong quantum mechanical effect. So when you go down to below 4 nanometer, shoots up, your surface potential shoots up, and it is not you cannot work in this region, right? I'm a process guy, so you can see that if you have three, say 3 nanometer, then where and then your process, of course, has roughly 1 angstrom's variation. Then your VT will change by 100 millivolts. How can you control that? My VT is for high-end CMOS is like 0.2 volts to point and 3 volts, and then my VDD is only 0.7 volts. I have no room for this large variation. So that's the reason, you know, silicon fin or SOI, the silicon channel has to be controlled um, to be not too small. You cannot have the silicon channel like 4 nanometers thick. Then you just get yourself into trouble. Let's be very clear about that. It's just FYI, right? Then they go to another options. Let's go to this silicon, this option B, heterogeneous epitaxy. Well, can you do this? Can you, you know, you end here? Here is not N gallium nitride first. Here is P silicon 111 first. So you put and then you do it together with gallium nitride on the same plane. That's wonderful. You can do that. But Intel find out that the whole mobility sucks. All right. The 111 is not good. It's not good. Electron it's pretty good, but the hole is pretty bad. And we want a good hole. That's the whole point because we already had a good N here. Gallium nitride is good N already. We need a good hole. And silicon 111 simply too low for this purpose. Right. So I'm afraid silicon 111 channel option is a no-go. Okay. Then but is a forever no-go? Well, there's a new paper just popped up. Not a new paper, but people mentioned that if you had this weird thing going on, if you could avoid uh, scattering, you could indeed have a 2D gas formed. You could form an ultra high mobility 111 in theory. In theory, so this is just why FYI, 1 degree Kelvin. It's not going to happen, but just fun to know about that. Sometimes things just like that. You have to know stuff. As a process guy, the more things you know, the better off you'll be. So the 3D monolithic, okay, is that okay? 3D monolithic is this case, which means that you layer transfer, you build your N first, is N first now, and then you layer transfer using a SOI or something. Then you grow your start to grow your epi silicon on top or your device on top. You still need bonding. And then, but you perform the subsequent processes after oxide layer transfer. The benefit is that there's a very high interconnect density, right? You could connect to the bottom with a process, right? You pattern it and dig a hole and connect. So you could do very fine interconnect, very high interconnect density. And then that's like your pitch could be as low as 50 nanometer. I saw something like that. That's doable, totally doable. And then the problem is that you have to build your device on top, your PFET silicon. That's fine, except one thing. You cannot have too high a temperature. You have to avoid your your process. If they demand a high temperature, will not hurt the gallium nitride below. All right. That's the only key concern. Is that true or not? That's difficult to say. But Intel data said, yeah, okay. Well, that's interesting. I would say that's interesting. But we don't know the yield, right? Until it's really put into HBM. On the paper say it's doable, some data is good, it's not good enough. And then last option, of course, wafer to wafer bonding, which is you perform, that's what we're going to talk about here. The last option is wafer-wafer bonding, which means that you have devices built separately. You build it and then you bond them. This is happening in packaging, right? Exactly happening in packaging. For Intel's EMB, IB, and then the interposer, everything is done separately, and then you bond them together with your bonding machine. This is good because you separate all the process separately so you don't interfere with each other. And then you could choose, by the way, you could choose whatever you want. Here you choose silicon 111 as a PFET. If you go crazy, you want the silicon 110, which is even better. And that's doable too. That's doable because you could choose whatever you want to do because you process your device, and this device separately. And then you bond them. And this is a wafer-to-wafer bonding. And then it's happening in process technology a lot. The only concern is what? If it's so good, why people don't use it? Well, because interconnect packing density. Right now, the bonding, this type of bonding can do about a couple of micron at best. So can you do 15 nanometer? Not yet. Okay, that people are working on. It's not an easy thing to do. If you could do it, yes. But right now, no. Okay, so I would say happy, half sad. It's not that simple. Okay, so this is summarized the Intel gallium nitride and silicon uh, their dream. And then you can see that most of them is gallium nitride on bottom with the P silicon on top. Okay. And then we're talking about the Raytheon. Raytheon is pretty much 200 millimeter. They I haven't seen it. They done the uh they've done the 300 millimeter. And they in a 200 millimeter they could do silicon 111 or silicon carbide. So this is what they can do because they could do silicon carbide. They could find silicon 200 millimeter silicon carbide by buying from Wolfspeed, right? It's available. So that's the advantage. If they go 300 millimeter, they go to 200 millimeter. Uh, then this probably the technology is much more easy to handle. And silicon carbide, the thermal mismatch. Let's look at what we shown earlier. See, silicon carbide here. They are lattice mismatch very small, the smallest among the three. And then the less thermal mismatch is also the most smallest, right? The silicon carbide has one of the best thermal conductivity. So you can see that the benefit of that, except the size. And then you could combine everything together. So it seemed they're doing pretty good. They did it, they processed this one. The outcome is pretty good from this report I read, right? And then they could do many things here. They of course they bound it. They could bound a CMOS with a gallium nitride on top of silicon 111 or a silicon carbide, right? So they demoed it. They could put CMOS to a very special function they're doing for the car, for the military. So they have many good stuff going on here, right? They have their niche, Raytheon, right? You know what they do, right? And then the bonding interface, they have a lot of energy. I see here, right? So this bonding interface, and there's a lot of work here. They already perfected. Uh, so to get a high yield, this is not an easy thing to do. Not easy to do. I said they shown here. At the end of the day, you need to get really good high yield. I think that's the story. And here, as another version of that, they spend all energy to bond a direct bonding interconnect. I have this one. I have discussed it very extensively on my previous talk in terms of copper bonding. So this one, they could do it. All right, so it's impressive, impressive. And this is another one, right, Weber scale, the MMIC with CMOS. So they are into this MMIC part of the 5G market, and they could do that. So for their communication chip, it's pretty good. And then all right, so this is interconnect. So we mentioned that already. Okay, so basically this is Raytheon's strategy. And they built their game on silicon. They had two machines, MOCVD and the MBE. MBE, 200 millimeter, they could do 300 millimeter. It's just a lot harder. Right? By MBE, you know that, right? Molecular beam epitaxy. These these were probably down in Texas somewhere, right? The it's pretty uniform. The way I see that, the uniformity is pretty good. And this is MOCVD. They probably got the tool from Extron and do a pretty good job. IQE, yeah, this company is very famous for generating high quality gallium nitride all using MBE or MOCVD. And you can see the key thing that interests me is that the wafer ball is very nice. This is a good number to have. The they are meeting their spec, uh, and imagine the MBE tool. An MBE tool have a very uniform temperature, or even MBE, right? This is 8-inch across the wafer. If the temperature is not uniform, then you will easily have a ball, meaning that their temperature control is very nice, impressive, impressive. Okay, so that's the Raytheon's stuff, and they they're competing in a 200 millimeter with a uh, different process and different wafers, but everybody has their own niche. Those are pretty good. Okay. Then in CFET, who's on top? I think the first question is that is this a process dominant question or layout related question? And who should be on top? And before I go, here I'd like to before I go to the complementary energy FET, let's look at this CFET. This is a CFET, the early version of CFET coming from Intel. That time they are talking about germanium as the PFAT. Germanium has a very, very good mobility versus silicon 100 mobility. And then the whole mobility I meant. This can go up to 400 or above. So they built it, they layer transfer this bonding oxide SOI, and then they build their N below with a FinFET, right? And then put the germanium PFAT on top. And this is, I think, impressive work because it's very difficult to get a pure germanium PFAT to work properly because the netting oxide is very bad. The passivation in the facial layer is very critical, not to mention the process. Germanium oxide dissolves in water. So it's not like SiO2 is so good, so strong. It can only dissolve in HF. It's, it's so good, right? But germanium oxide is naturally pretty bad. And there are two approaches for this one. As I mentioned, the Intel one is Intel one is a germanium 100 layer. Here is a 100, and then with a layer transfer. So they build device on top, kind of monolithic. And KAIST is Korea best high tech university. They have interesting papers. Say, well, you do 100. Well, I'm going to do 110. It's the same thing, monolithic 3D. Then they demo it work for them, and let's discuss the pros and cons for each one. Intel's process, they demonstrate their layer transfer germanium depends on the carrier concentration, the high carrier concentration. They could do 400. See that? This is close to the silicon 100 very nicely, very nicely. Okay, higher. So this is good, very good. And then for the low density, they are much higher. Wow. So this is they have achieved that. By my buddy Rahmadi did it very nicely. And KAIST, they have used some interesting technique. First of all, their layer transfer, they use yttrium oxide. In here, obviously, they use regular silicon dioxide, the box. That's pretty much it. This is and Soitec make that, right? They could buy by Soitec or someone else and buy the SOI wafer. And the KAIST did it different. They put SiO and then yttrium oxide together. Yttrium oxide is very tough material, very good, very high Ag as well, and many unique properties. The decided to put the device on top, and then of course, and then they flip it, and then they start to have to put devices on the germanium layer. This flow is quite straightforward. The only thing that concerns me is that the temperature. You can look at that. Everything they do is ultra low temperature. They're talking about 250 because they're afraid of damaging the germanium. But you know that, right? So the device, this is only demo it worked. It's really not a good idea to have 250 because if you put copper on top, if you put a real world device, you had to put copper line back in the line on top of germanium. Those process copper copper back in line, they have to be about 4 to 500, right? They will not go above 500, but definitely go above 400. So imagine you put a lot of copper line, many layer on top of this one, then the device will be killed. So these are all useless stuff. Unfortunately, it's good for demo, but in real world, probably not going to work. Then let's come to the CFET, recently the hot topic, the complementary FET. It's a nanosheet FET, and then you stack of N nanosheet on top of P. This time P is on the bottom, and then the N on top. The folding of the N and P in here. See, CMOS, you have the side by side, the N and P are side by side, so they have the area, they have the separate part, they have the separation. But you now fold them together, then you save the space. This folding space, all right, after you fold it, in this case, P on the bottom and on top, you save the folding space. And if you enable that by connecting your contact, here the bottom is PMOS, you have a bottom contact on the bottom, and top contact on the from the top, then the total area selection will be very nice. Then why P on the bottom then? Well, it turns out that people just seem to agree that the process, this PC stress engineering seems easier if you put the SiC on the bottom. I will discuss about why that's not a good idea from a process perspective. It may not be a good idea, right? And last time we discussed about you have to, and here, as I mentioned, you have the backside contact. To do the backside contact, then the backside power delivery is these BSPDN come to mind. Intel call them power via, and then it's showing that wow, here this frontside contact, they move it to the backside. That's great. The reason is that you can access to your channel, your transistor much closer. See this thick copper line? The resistance is a lot smaller. And here, imagine your voltage VDD 0.7 volt had to travel all the way down here, touch your transistor. And then when you go down, the copper line get thinner and thinner. So you're losing your IR, you're losing your voltage. The whole point is that getting your 0.7 volts all the way down to here without losing much. That's the whole idea. And then you cannot do that for the 3 nanometer, beyond 3 nanometer anymore. That's just a no, right? And then the earlier you put it in, the better. Okay, so Intel say they would do it for 4 nanometer. But they are no customer yet, so I don't know. They have to do better. Even though their technology is much more advanced than the other two, but they are in competition. We'll see who wins this war. And here is their PowerPoint. Very nicely demonstrate that with their design, the backside via the power via backside PDN can reach your device much very easy. And then he solved also the signal routing M1 and M0 problem. And you can see that the IR drop, the FX, they're going to significantly uh, improved, or the 30% and all that. So is that real? Is that real? Well, this is Prime Material said is real. 30% 20 to 30% improvement. That's what they claim. And then will that be really? Uh, I don't know. Okay, to be frank, I don't know. But TSMC recently had the news. They say 10 to 15. It's half of what they say here, right? So that's be very careful about that, right? So the the this is the benefit of backside cell PDN. They really can reduce the cell area. So it seems settled that the and PFET will be on the bottom. But PFET, it's I would say Achilles heel, like Achilles heel for the most CMOS because the whole mobility, the inferior mobility, and the doping is bad, and difficult contact, and the complex stress engineering. So let's discuss about that. Before we go, let's do some fundamental fun things, right? So how fast are electrons? The drifting, we call it drift velocity. If you look at the copper wire, you think electron would move very quickly inside? Not so. They move very slowly. They move 1 second. They move 1 centimeter in about 1 second. So that's kind of super slow. But the drift velocity in a semiconductor is million times better. That's the reason we use it. Right. So this is so just to get to gauge everybody about that. So electron is pretty good, but hole is not. Well, it's still moving relatively quickly, but compared with the in the copper wire, but in the world of semiconductor, they are not that good anymore, right? So their whole mobility is much less than uh, the silicon. On top of that, the uh, well, the problem is that at a high field, they'll drop like a rock. You could look at this universal curve from Takaki. You could see that at the one, I took a typical value of one, right? This one megavolt per centimeter. And this one here, you can see the electron mobility is 250, and then the hole is like 60. So it's 4 times less, and that's a problem. Or that's a problem. And so what do we do? So people say, well, you could do 110, right? 110, you can see from the right graph, 110 has a much higher hole mobility, and that's a good thing. So this one, that's the reason in FinFET, we move our uh, channel direction so that the channel plane sees 110. The carrier are moving along the 110 directions, 111 plane, 111 directions. And that's pretty good. But again, why hypothetically in high level, why 110 had a higher whole mobility? Well, because you have this less whole electron mass is smaller. Well, that's kind of a quantum mechanical effect. But what I like to give you is that it's because of density. It's a simple explanation. You can look at the that's my personal opinion that 110 uh, atomic density is 9.6 atom per nanometer square. And then look at 11100, it's only 6.8. So this is like 30% better. Right? And then why would that matter? Well, the 110, because how electron moves, electron hole move differently. Hole move in a way is kind of cascading against electron moves. When electron move away from its lattice, then there will be hole leaving behind. And the whole move is like an imaging force of silicon or electrons. And 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 you could also imagine that whole moves if there's a lot of space around. So it could move to, that's where the high density come in. Then it's easier. It turns out it can be easier, a lot easier. But can it be easier than silicon? Well, it may not be. Let's look at these pictures. This is if you have the immersion, inversion density 10 to the 13 here. If you look at the comparison, uh, of course, 100, 100 is a round circle, and here in P regular, this is 100, right? So your hole is not good. And then here your N is pretty good. And if you do 110, which is a square, right? A square here, you move up. Pretty good, like 2x. You move on at 2 to 3x, right? Close to 2x. But look at the axis. Don't be confused, right? So people, I mean, the publisher, the author like to change their axis in a way so that they look similar in scale, but it's not. Here, if I check the actual value, you always do that. And 1 E13 centimeter squared, this inversion density without doping, all right? Here you have 160, okay, 160, right? And then you look at the hole here, 260, 270, right? It's still small. This one is smaller than this one because the scale. So be very careful. Okay, you always check that the y-axis actual values. And then and then so what's that to do with nanosheet? Well, nanosheet you lost the 10110 benefit because your nanosheet is flat. Your surface is 100, and your FinFET, your surface, you buy a wafer is 100, but you are cutting the wafer, you're etching the wafer to form a fin, and that fin can be oriented in any direction you want. And you choose the FinFET 110 surface for your fin. So you got a whole benefit. But you cannot do that in your nanosheet when you come with a 100 surface. Well, then the question is, can I do 110? I mentioned, CFET, we could change the crystal orientation, right? Well, in theory, you could. But the problem with that is that it's very difficult to do epitaxial growth on 110. This is because there's many people study that. They find out the fundamental reason you cannot do that properly is the 110 growth rate is bad, and then you are easy to form many dislocations. The theoretical critical thickness for epitaxial on 110 is very small, much smaller than 100. And then your H2 pre-bake, you had to pre-bake to get rid of silicon dioxide, the navy oxide, and that will wrinkle the surface and that make defect. So okay, you could see that. So it's not easy thing to do. People try, IMEC try, Intel try, TSMC try. None of them are very successful. Okay, so that's the fundamental problem. And fundamentally, PFET inside a CFET is still weaker than NFET, right? Even though FinFET is the same thing, right? It's just a little bit better than nanosheet Nanosheet is a lot worse. And then because the GAA has a 1010 surface, by nature is pretty bad. So if you look at the devices, this is even the simulation one too. This is simulated one. The MFET on the bottom, I mean PFET on the bottom, MFET on the top. And look at the devices, you can see that the current with the same layout, the current ion with the same here same ion. You can see that is 1 point. This is 15.3 micron versus 21.6 micron. Okay, so you can see that this is much smaller, and you have a mismatch in your ion. It's very difficult to make a good inverter. So your SRAM will be screwed, right? So you have to do something. You have to do something. What do you do? Well, you have to put a stressor there, okay? And that's what you need to do. You have to put a good stressor so as that you could improve your device. This is a nice ECG source drain technology, pretty much invented by IBM, but perfected by Intel. And the other one do it could they take IBM's innovation and make it into their own, and do a very good job on that to make yield high. So they are the forerunners in ECG source and drain technology. It's a stressor. You can see that the size. CG, they squeeze it. They have a compressive strain uh, in the channel. Each channel, the germanium atom is larger, so they have uh, a larger compressive stress induced by the ECG embedded silicon germanium epi. And that time, in the early days, in 90 nanometer, germanium is 18%. And then eventually going to recently 22 nanometer or beyond has to be at least 55%. Now, the more you do, okay, the 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 higher germanium had coming in, and you can see that. You can see the germanium. It has to be recessed as well. Keep that in mind. This is important too. It is important too. And then and, and for the 32, they even have to raise the source and drain. They have to make it even taller to reduce uh, the resistance, contact resistance, right? You're doing that too now. Okay. But from the stress perspective, I think this from Professor Xu did a very good summary using Mora's simulations. If you look at the evolution of stressor, when you just formed, actually it's kind of like a tensile. Okay, they are not compressive. And then when you have a different process come out, and then eventually this is I'm talking about the longitudinal stress or strain here, x directions. Okay, this is what I'm talking about. This is the channel directions as a longitudinal. You can see that initially they seem to be tensile, and then they go eventually form into after you high K you become uh, compressive. So let's be very clear about that. That's that thing we need to keep in mind. It's not like initially when you put ECG, boom, it becomes compressive. That's not the case in many ways. And this simulation shows that even you finally formed, but look, this strain here, look at the paper. I mean, look at your calculations, seem very good. It will give you a couple gig Pascal, but in reality, it would not, because here you have the dummy. These are all gate. Before the high K mirror gate last process coming in, they've been squeezed. Even though you're compressive here, but it just won't take it. All right. The channel just don't fit it. It won't be changed because they are sticky to something else. So they don't change, right? The strain is not happening. If you would say, I will put germanium 55% here, this is strain I'm going to get. Well, I'm sorry, but channel will not listen to you. They've been held on by something else. So how do you get your strain back is that you need to remove the gate. So the dummy gate, once the dummy gate removed, they relaxed. Boom! You see that the blue thing here. Initially, it's a little bit here, little bit here, and boom, you have the dummy gate removal. Then that's where your strain coming back. All right. So this happened. That's the gate last thing. Initially, the gate last thing is designed for protecting your high K because the high K here, if you don't do it, right, you never remove uh, you never remove your gate last, your gate first, you're not gate last, then you will be in trouble, right? Your high K will be damaged. The high K metal gate, and then the last you put a high K here now, then you put a metal gate on top. You could change your metal gate any way you want it, right? So you have a good way of tuning your work functions. So you have multiple purpose for your high K metal gate. You change your high K, and then you modify your metal gate at will, then you could do a lot of job that you want them to do. But this process has a hidden profit benefit now nobody anticipated until they do it. It's because the free space exposed here, this strain relaxed, not strain relaxed. It's just free space that the surface silicon channel can relax now. So that means that your ECG can work properly. That's the beauty of high-K metal gate. It's a side benefit. But these days, everything affects. What we just mentioned, yes, true. But right now, when you're scaling, your source and drain volume reduced. And then metal gate last, yeah, this is not last, this is previous, right? And layout dependency, NAND state or isolated with a tensor, and then contact, silicization, medical itself, everything impacts Si&Ge and the process. So that's this thing we want to keep in mind. So volume reductions, stressor. If you look at the using the, this is the SOI case. SOI has very thin channel, right? And then the source and drain is smaller because you have a very thin channel in the beginning. So to squeeze that, so squeeze the channel, squeeze the strain here is very, very hard, very hard. So you got less benefit because source and drain is small. So you had to make it much larger in order to get your benefit back. Okay. And then the SOI FinFET, well, that's it just that one you need a big, right? Just like any FinFET, this is SOI FinFET, but you still eventually had to use a larger volume. So Si&Ge volume matters. When you scale down, your device becomes smaller, everything becomes smaller, and your strain effect by nature is small. And then, but this one's still there, right? So I just want to remind you that the middle gate lag, that benefit is still there. That's good. Then, so FinFET wise, it has a unique benefit against the current nanosheet FET is that when you grow its Si&Ge, you grow from all the surface in a nice wet manner. You could do it properly without any defect. And in the strain, you can see that EZZ here, right? Fin on the bottom because it's squeezed here, right? This is your EZZ squeeze here. It's small. The volume is small, so it has a smaller. And then the top of the fin is much bigger, right? Small in a way is relative. It's just like see here is -1, like half of it, and here is like 2. right? So it's just reasonably small. Okay, so, but it got a pretty good strain on the top of the fin, and that's where this current go in, right? And and FinFET has been developed, is very mature, so this thing worked nicely. Okay. It, but they still have problem. In fact, I still had problem. P stressor is very sensitive to his neighbors and doesn't like to live alone. What I meant is that you could see in this simulation, actually happening in real life as well. The nested FinFET, the strain is uniform. Okay, so the Si&Ge, and they squeeze this one, you could reach about 1.2 gigapascal. Very nice. And with that, you boost up your current to a good number. But if you have isolated one, right? Isolated one, then this source and drain, they put it here, but it will not create strain here. So why is that? Because the strain, uh, to make Si&Ge work, if both sides has to be have a super high, super good strain to restrain silicon germanium in a way so it could push forward. But imagine if this here is like an open door, then your strength, you're losing your energy on your isolated FinFET. This area is kind of empty, right? Space. There's no strain here. So they will go with that side. So there will be no strain here. Be no strain here. Here become positive, become tensile. It's not even compressive. So you can see that it had a strong layout problem. It's very sensitive to its neighbors. It like to be squeezed. Okay, like to be squeezed. Living in a very crowded area is nice. If it's living alone, it doesn't work. Okay, so P stressor as an additional complexity in nanosheet FET. This is FinFET case. It already has some complication as we mentioned here. Right, so you need to be high-K metal gate last. All right, you need to be in nested FinFET more and isolated less as much as you can. Otherwise, you won't get your currents. And then when you come to nanosheet FET, it's making much worse. The reason is this. Because if you look at nanosheet FET, the source strain epi, it grows from multiple surfaces. In the FinFET world, you grow everything from the same silicon surface. So you could have a nice epi. But on the nanosheet FET, here is your channel. That's silicon. And here is your inner spacer. So you see oxide or nitride. So when you form this type of epi, it's naturally defective because it grows from multiple fronts. It's not grow uniformly from one front. It's grow from multiple fronts. So you will merge, it form a seam. You will form two types of seam, vertical seam and horizontal seam. This type of seam, we have seen this in epi world, seen this a lot. In here, I present to you 1994 paper, the the ELO epi, epitaxial lateral overgrowth. So you grow epi from the both sides, right? This oxide, and you grow epi from the trans here, and you merge. When you merge, because there's no perfect match surface, you always has a mismatch. The merging interface or the merge interface always has dislocation. It could be threading, could be something else. Could be stacking for, depends on conditions you grow, right? And then if you look at uh, the growth of the forming of one single defect. My title is that one defect ruins your stress engineering. What do I mean by that? Because one dislocation He says Berger's vector size is like couple of angstrom. Right? 5 angstrom is a nominal value. And that means that's an empty space. And then what does that strain correspond to? See, Si&Ge, we're talking about 1%. It's difficult to form a 2% strain. So it's not 1%. 1% is what? Is 1%, 0.01 times your source strain size, right? And that's like, I use 50 nanometer, right? So that is 0.1% of 50 nanometer is 5 angstrom. It's 0.5, is 0.5 nanometer. So, and then you have 1.5 nanometer of empty space. Your Berger vector dislocation is a mismatch of the plane of a line. And then the second four is a mismatched or half line. And those are empty space you can imagine. So it become a 100% relaxed. So your strain, 1% of strain, you're supposed to go to a formed by perfect crystalline. But if you have one defect inside, you no longer have the luxury of generating 1% of strain that you desire to. You have zero strain. Your strain being eaten up by local relaxations. And simulation says 25%. Here I'm just using a rule of thumb calculations. And then the simulations, 25%, but that's beyond the point. Right? Your simulation here, when you generate one defect, actually usually more than one, right? And then in CFET, Si&Ge epi from multiple surfaces, right? They go from multiple surfaces, and then they form many stacking faults. And then this is uh, this is a problem we have to deal with. And then on top of that, here is another one. The silicon nanosheet actually is formed differently than the FinFET. FinFET initially, when you cut it, is like in a free space, right? You is no strain. But silicon nanosheet is formed by removing the Si&Ge layer here, because initially they are tensile strained. Let's keep it in mind. So when it forms, when it just form, it's actually tensile. Positive value means tensile. They are not compressive. So, and then you need to form a sausage ring around it in a way to make it compressive. Initially, it's tensile, so you need to do more work. You need to do more work for your stressor, right? And your stressor right now is more defective. That's a big problem, right? The stressor now is defective, and then your silicon nanosheet channel is actually bone tensile, and that's bad, right? You can imagine that's bad. And on top of that, here's the simulation from AMEC is very interesting. It says that if you form, it depends on the defect, because the vertical defect here, vertical stacking fault and horizontal stacking fault, and you have also a free space here. With that, you could form in a different conditions, sometimes tensile, sometimes compressive. This is what you want. But in certain conditions, you could form tensile. Imagine you have a device, and if you cannot control, then that's a big problem. That's a big problem. So no wonder, okay, these PCE source and drain before N silicon, I would say is not ideal for junctions. The problem is that in this case, Si&Ge channel, Si&Ge source and drain on the bottom had not only the defect issue, but also temperature issues. You look at the picture on the right here, the boron here. Right, here is steel silicon, but if it Uh, but in the future, here is a Si&Ge. Silicon boron is fine. But if you move to Si&Ge as Si&Ge stressor, the boron diffusion is very temperature sensitive. This means that your high temperature in N-Si&Ge, I mean N source and drain, which is silicon, your silicon on top, right? Silicon on top here. The temperature for forming source and drain is a silicon SiP process. Silicon SiP process is reasonably high temperature. And that high temperature, the thermal budget, the thermal histogram will diffuse the boron inside the silicon germanium. The boron's diffusivity is higher because of germanium, right? And then that will change your junctional properties. So that's the one of the problem I see here. It's not an easy thing to do. So the defect, as we mentioned here, the defect will the stress and strain defect will have it will change your strain, could potentially change your strain from compressive to tensile. That's not what you want at all. Or uh, or the germanium on germanium on the bottom could uh, re, could force you to reduce the temperature of source drain on the top. It's not a good thing, right? You need to activate your source and drain. So all the temperature has been optimized. And then you're not restricting their temperature, then you are reducing your activation efficiency. So that's not good. But so the bottom line is this: one cannot rely solely on silicon epi for stressor in the nanosheet CFET. And then there are other not. Fortunately, as I mentioned here, there are many things you could do to get your stress back. PCG, you have problem. PCG, you have problem. So you need to, at the end of the day, the process guy had to identify a special process. Here I mentioned the sensitization. And this one will change you need to do nickel silicide, right? You need to change the strain very big, right? So all these had to comprehend. CISO may not, but NCSI, yes, right? So all these you had to play around with it. The metal gauge could change your stress too. And the reason I mention is that the dimension becomes so small. So everything affect more effectively now. Even though Si&Ge is not good, all right. But remember, you have a Si&Ge recess, as I mentioned here in the early presentation. The evolution of the evolution. I think I missed that page here. See the evolution of FinFET, the Si&Ge evolution, you have to have a Si&Ge recess. And here you need, of course, volume, right? You need a surface area. But at the same time, you reduce the Si&Ge volume. So the effective mode, the way I see the Si&Ge volume has some effect, but the role of Si&Ge volume may not be as big as before, because just simply because the amount less. And it's just good and bad, right? You really rely on it to give you strength, but it give you more variability. So bottom line is that you need to figure out how to modify or apply places around this area to give you the strength you want. Is it doable? I think it is. Which is that, well, who's going to win this game? TSMC, Samsung, or Intel. Currently, TSMC process technology seem leading, but you never know. Never know. So this one we'll wait to be seen. All right. So this is uh this is my talk here. My talk here is that who gets on top this time? Case study of silicon germanium. Remember we talked about P germanium on top of N silicon, and then gallium nitride is usually on the bottom, and then on 111, and then you put P-channel silicon on top. And this one, you have a lot of a Si&Ge problem because of nanosheet FET. No wonder right now the nanosheet FET get around that TSMC will not do it at 3. It has a lot of processes you need to overcome, and they will do it too. Samsung, on the other hand, is starting with 5 and then drop to 4 and then the 3. So they are early runner for the nanosheet FET. But nanosheet FET has so many problems. So, and that is the Samsung, one of the reason why Samsung process yield for the nanosheet is lower than the TSMC. TSMC just all the way to they're gonna squeeze the last juice of FinFET, right? They follow the Intel's idea. They keep using it. It's difficult to change architecture. You change architecture, you pay the big price. And here, nanosheet FET Si&Ge is so hard to do, so hard to make it perfect. In addition to other problems that we're going to talk in the future, the yield is naturally low. So it takes us some time to make it work. Okay. All right. So that's my talk. Thank you, everybody.